Okay, I think that's been enough examples for the moment. Now let's finally come to the definition of convergence. So now we are really ready for it. So we have a metric space, XD. Right, so X is some set, not empty, and D is a distance function, a metric. And we have a sequence x1, x2, and so on in X. And another element X in X that would then turn out to be the limit. Okay, so we say xn converges to X, write xn arrow X. Sometimes you also say as n goes to infinity. Well, usually this is clear. If there's only one index here that is able to run, then what else should happen? If the distance of xn comma x goes to 0 as n goes to infinity. Now you might find this a bit cheeky because we are defining the word convergence by using convergence. So is this running around in circles? It's not if you know what the last convergence means. This last convergence is just convergence in the set of real numbers as you learned it in your analysis 1 course. So you can spell it out as follows. Yeah, what is it? I mean, last week it's been linear algebra all the way. So now analysis, do you remember? It means for every epsilon greater than 0, there exists a little n, maybe let's call it n0, such that for all n greater than or equal to n0, you have d of xn comma x less than epsilon. Right, you remember? So for our sequence, this means if this is the point x, the limit where we are claiming to converge to, and this is my sequence running around somehow, I'm claiming this converges to x, then what am I saying here? I'm saying that for every epsilon greater than 0, so no matter how small I take my epsilon, and epsilon is reflected by a little, it's the radius of a circle that I'm now drawing here. Well, this is supposed to be a circle. There exists an index such that for every n after this index, I'm inside the circle. Okay, so it's, in our case here, it's not, you think after this point you're always inside the circle, but it's not quite true. You are leaving the circle now and then. You're leaving it here and here, and then again here, 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 here. But after that one, you're not leaving the circle anymore. Okay, so this is your n0th point, which is then your x n0, and for this and all the others that are coming, you're indeed inside the epsilon circle around your point x. If I say circle, then I just mean the set of all points for which the distance from these points to the midpoint x is less than epsilon. if this is really a circle, of course, depends on your metric. We've seen funny metrics above, and for some of them, the result might look very different from circles. You could play around and see what circles look like in the French railroad metric. They will probably not be usual circles, rather French circles. What's a circle in the discrete metric? Well, it probably depends on the radius. If you ask for a circle of radius 2, so if this is your point x and you're asking which points have distance less than 2 from my point x, then the answer is going to be, well, the whole plane, everything, because distances can only be 0 and 1, so they are always less than 2. So that'd be a huge circle, right? If you ask for a circle of radius 0.5, what would you get? Well, you only get the point x itself, because that's the only one whose distance from x is less than 0.5. Okay, Hamming distance. Difficult to draw, of course, because we're talking about n-bit numbers. Well, here in the Euclidean distance, you would get the usual circles or balls if you're higher dimensional. Okay. I think that's enough about convergence. We say that a sequence is often abbreviated like that. N equals 1 to infinity, or sometimes you would even drop the n equals 1 to infinity. The sequence is called convergent. Well, if it converges to something, right? If it has a limit. If there exists an x in x such that xn converges to x, right? Remember the funny upside down e? It means there exists. Okay, just some very simple examples to recall the notations. Let's take the space equal to the real numbers, and so this sequence of real numbers is a convergent sequence, right? So I'm just taking 1 over n is running through the natural numbers, and this is convergent. How do you prove it is convergent? Well, you say what a limit is. Okay, you say because it converges to 0, and it's easy to check it is. Okay, that was the first example. Next example, 1 minus 1, 1 minus 1, and so on, is, I would say, is not convergent, right? Is not convergent. Seems pretty obvious, but how do you prove it? I mean, it's not convergent to 0. I think we can see that. It's not convergent to 3. It doesn't converge to 5 though. But you couldn't try for all real numbers and then say it's not converging to any of them, so it's not convergent. You see, this is troublesome. So showing that a sequence is not convergent means you would have to try for all possible limits and rule them all out, which really sounds too much to be done. So you somehow need to be more tricky or more clever here. You could try to draw the situation here to envisage what the sequence is doing. I mean, it's jumping back and forth between these 2 points. What is that telling us? I mean, if a sequence would converge, right? Let's envisage that situation. So here's my limit, and suppose I have a sequence that converges to this limit x, then my elements xn would not only would their distance to x go to 0, also their distance to each other would become smaller and smaller the higher you have these counting numbers, these indices, right? So you would not only, so if xn goes to x, then not only the distance of xn to x goes to 0 as n goes to infinity, but also the distance of xm and xn goes to 0 as m and n both go to infinity. And this last property is pretty cool because you can check it without the need of a limit, right? So to check the first property, convergence, you always need the potential limit x, otherwise you cannot do anything. You do not need this to check the last property, right? So this one can be checked without any potential limits. And for our sequence here, this is clearly not true because the distance of 1 and -1 doesn't go to 0. It always remains 2. No matter how far you count, it's not going down to 0. And here we have this implication. I hope you can still see it. So there's this arrow. If you have convergence, then you have the right property. So if the sequence would converge, then it would have the right property. It doesn't have the right property, so it's not convergent. See how clever this is? Because it's so clever, the red property gets its own name. It's not called the red property anymore. You give it a name. You say definition. So we are in a metric space. And you say that a sequence in X is called a Cauchy sequence, named after French mathematician Mr. Cauchy, if it has the right property. So let's write it down again. So if the distance of xm and xn goes to 0 as m and n both go to infinity. Should we spell that out with epsilons and stuff? That means if for all epsilon greater than 0 there exists a counter, let's call it again n0, such that for all m and n greater than or equal to n0, you have that the distance of xm and xn is less than epsilon. Okay, so while convergence says my elements, the elements of my sequence, are coming closer and closer to the limit, this one is not even talking about a limit. It's just saying as m and n are getting bigger, the elements xm and xn are coming closer to each other. Completely different story, almost the same meaning. We set it up here. We said that if your sequence converges, then it is a Cauchy sequence. This is indeed not difficult to prove, but let's leave this to people teaching analysis 1. We cannot recall all of analysis 1 and linear algebra 1 and 2 here because we want to make some progress at some point. So important. If xn is convergent, then xn is a Cauchy sequence. Okay, you see that if you're getting a bit excited, then you're starting to drop the little indices down here and up here with your sequence, but still everybody knows what we are talking about. So this will happen more and more often in the future, and you still know what I mean. If I'm putting the brackets around, and I'm not talking about the particular element xn, I'm talking about the whole sequence that you get when n runs through the natural numbers. Okay, very important thing. Whenever we see an implication sign like this, we tend to ask ourselves, how about the other direction? Wouldn't it be great if also the other direction holds? Then we could say if and only if. While on the other hand, then we would have two different names. One is convergent, the other one is Cauchy sequence for one and the same thing. That would be stupid. So probably it doesn't hold the other way around. Let's find examples.